Hello dear students. In this video I want to solve again the problem with the method of two-phase method, okay, to help you understand better this method. So before starting this part, just let's review together what are the different forms of the problem that we can solve. Okay, so in our objective function, as we talked before, we can have maximization or minimization. Okay, and if in terms of our constraints, we have three different forms. Yeah, you remember less than or equal, greater than or equal. Okay, so as you remember, as I told you, for each of the constraints of the problem, we have to define, okay, one basic variable. In the case of less than or equal, we talked by adding one slack variable, we have this basic variable. In the case of equality, we talked, we add one variable that we name it artificial variable, okay, to have this basic variable for this constraint. And in the case of greater than or equal, as we talked, we have one surplus variable. For example, we have left hand side greater than or equal to right hand side. By subtracting one variable that we name it surplus variable, we make it equal. But as we talked before, because this surplus variable could be negative if the other variables, original variables, are zero, so we need to have we have to have a new variable as basic variable for this constraint. For this reason, we added another artificial variable. So pay attention. Big M method or two-phase method are not new uh, types of solving problem. All of these problems can be solved via simplex method, but in the problems that we have greater than or equal, first of all, we need to add these variables to our constraints, artificial, surplus, whatever, okay, and we need to make changes based on our uh, artificial variables in our objective function, and then apply uh, simplex method. Okay, so we solve all of the problems through simplex method. First of all, we need to make some changes in our objective function. Why do we make these changes in our objective function? So you remember the definition of artificial variable. Artificial variable, as its name says, it's a variable that doesn't exist. Okay, so when we add this one in our constraints to neutralize, okay, and to eliminate the effect of this one in our final solution, we have to see this one in our objective function based on the big a method that I told you to solve this problem. Okay, we penalized our objective function based on a very positive big number that we named it m. Okay, but in the case of two-phase method is exactly the same but in a different manner. How? Now let's pay attention to this problem that we have. It's the same problem that we solved it via big M method. That you see, it's a type of minimization, the radiation therapy problem. Minimization of z equal to 0.4 x1 plus 0.5 x2. We have three different constraints. As you see, the first one is less than or equal, the second one is equal, and the third one is greater than or equal. So based on what we learned, we need to add one slack variable to the first one, we need to add one artificial variable to the second one, we need to subtract one surplus variable from third one and add one artificial variable to the third constraint. So, attention, if I write this one in an augmented form, okay, augmented means by adding this one a bigger form, our constraints, okay, should be something like this. Okay, we know this part. But pay attention to our objective function. Okay, before we had this objective function, this one. What happens here? Here is the first phase of two-phase method. As you see here, phase one. It means that we should form the same type of the objective function. It was minimization, okay? And based on the number of the objective functions, the artificial variables that we have, we need to define our new objective function for our problem. Why? Because we want to eliminate the effect of these artificial variables to our problem and move to the first feasible solution in our problem. Okay, and based on that, we try to improve to find the optimal solution of our problem. Okay, so how many artificial variables did we define in our constraints? 1 and 2. So it will be x4 bar plus x6 bar. Okay, so this is my new objective function with the exactly same uh, constraints that we have. So in the first phase, okay, the first phase, we have this type of problem, okay, we have this type of problem as you see, okay, as you see, this is the type of the problem that we have and we need to solve it. So it's exactly like before, but to this end, attention what we should do. Let me change the color of my pen here, guys. So of course I don't change this one, is minimization, okay, no. uh can I write my objective function like this? X4 bar plus X6 bar equal to 0. Yes or no? Sorry, minus. X4 minus X6 bar. So, wait a moment, please. Okay. And we want to define our objective function and eliminate this effect of this constraint, okay, this artificial variables in our objective function. Why? Because imagine, for example, here and here we define our basic variables x4 bar and x6 bar, but as we know, the coefficient of these variables in the row of z should be 0. Are they 0 here? No, they are not 0. They are 1 and 1. So we need to change these items, okay, convert them to 0. How do we do this one? Exactly like what we did in our big M method. For example, if I name this one 0, if I name this one 1, 2, and 3, we see the existence of 2 and 3 in our problem, okay, in our problem. So to this end, if this one is 0, the 2 is 0.5 x1 plus 0.5 x2 plus x4 bar equal to 2.7. Okay, the same happens for the third one, 0.6 x1 plus 0.4 x2 minus x5 plus x 6 bar equal to 6 is the third one. So to eliminate the effect of this, the coefficient of these artificial variables in our objective function, what should I do? I should, let me change this location. I should simply multiply these two constraints in one, okay, because here I have plus x4 bar, I have plus x6 bar, and add these two constraints multiplied by minus 1, sorry, plus 1, and adding to row 0, the key formula. We need to calculate 0 plus 2 plus 3. Okay, so if we calculate these items, okay, as we see, our artificial variables don't have any uh, coefficient in the line of z, and we can start our problem. So I repeat, either big M or uh, two-phase method are methods, okay, to eliminate the coefficients of artificial variables in our objective function. So let me show you the complete form. Okay, if we see in this problem, okay, pay attention guys, this is the first table converting the elements. So as you see, just let me show you here, 0.5, 0.6 give me 1.1 multiplied by x1. Here 0.5, 0.4, 0.9 gives me, and the rest. Okay, so because I didn't change this minimization to maximization, okay, I need to continue with this form. But as you see in this table, the problem tried to change minimization to maximization. We talked, if we change minimizing z to maximization, the formula will be maximization of minus z. Okay, so the result always is similar, is totally similar. Okay, what is the only change? To select the most negative one in the maximization and most positive one in minimization. So imagine if I continued with the same objective function, plus and plus, again my entering variable is the same, okay, because plus 1.1 is the most positive variable as an entering variable. So there is no difference in these two type of problem. So imagine we just multiply this problem, okay, in one negative to understand better the table, and we follow here the maximization of minus c. Okay, so we have this first table. As you see, the coefficients of two objective function artificial variables now are 0 in our objective function, and the table is ready. Okay, so we follow simplex method every time to find the optimal solution, to find the first feasible solution. Okay, so as you see, because we want to maximize here, every time this z becomes bigger. Or imagine if it was minimization, it was 12 to 2.1, again minimizing. Okay, and in this case minus 12 to minus 2.1 maximizing. Okay, so we continue this one, as you know, in the maximization until we don't have any negative element, or if we continued with maximization until we don't have any positive element. So as you see in this table, what is the problem here? Okay, nothing. in this problem, in this table, as you see, for the third table, we don't have any negative values in our objective function line. And as you see, this -1 shows this is minus z, okay, -1 by z, okay, or we can uh, directly write here, if we solve this problem, something like this, minus z, but they are exactly the same, as I told you, or in the manner that I write the table, or like this, both of them are correct. One important item, so as you see, this 0 now is the first feasible solution for our problem. So this is the final table of our first phase of problem. Now for the second phase, let's go back to this explanation. When we find the result of the first table, okay, first phase, sorry, we need to solve this problem. What is this problem, guys? Exactly the same objective function that we had before, and our constraints, okay, our constraints without without artificial variables in our problem. Okay, so this is the second phase that I ask you to write. But how to do this problem, okay, in this case? Very, very easy. How is it? Imagine this one is the final table of the second phase, the first phase, okay? So for sure, this table 3 is the first table of the second phase. Let's see what happens. Imagine all these numbers and remember all of them. So the final phase tableau, okay, or table of the phase 1, as you see, is exactly the same that we had before. You need to repeat and do some steps here to prepare the table for the second phase. How you should do that? You should drop the line of x4 bar and x6 bar. Okay, imagine they don't exist because we solved them and we already calculated them, and just by use of them we try to find the first feasible solution. So we drop this one, as you see, instead of 1 2 3 4 5 6 columns, now we have 1 2 3 4 sorry, 4 columns. Okay, so the next, we need to substitute our objective function. We know that our objective function is minimization z equal to 0.4 x1 plus 0.4 x2, 0.4 and 0.5, sorry. So what happens here, guys? Up to this point, we just substitute some elements, okay, and drop some items. But now what should we do? Let me clean this part. Okay, what should we do at this point? What are our basic variables? X1, x3, x2. In each step, the coefficient of basic variables should be 0 in the line of z. So, but here, as you see, the coefficient of our x1 is not 0, is 0.4, or the coefficient of our x2 is not 0, is 0.5. So we still need to make the last change. How we do this change? We need to convert 0.4 and 0.5 to 0. How should we do that? By using our objective function. Let me again write this one. My objective function 0.4 x1 plus 0.5 x2. Okay, so as you see here in the objective function, my x1 has the coefficient of 0.4 and my x2 has the coefficient of 0.5. Okay, so it means that if I multiply them in one minus the lines that we have x1 and x2 in minus 0.4 and minus 0.5, okay, here better show this one, and this one. If I multiply them in minus 0.4 and minus 0.5, we can eliminate the effect of this item and have the objective function of 0 and 0. Okay, so now this is our right hand side. Why this one is minus 0.5 for minus 5.4? Because in this case now we are maximizing minus z, so our z is 5.4. Okay, so now the table is ready to find the optimal solution. Is the solution is optimal? No. Why? Because in this row of z we still have one negative item. I repeat, if I did this one by minimization, here I should have had 0.5. Okay, and no problem, because in that case of minimization still it was not an optimal solution because we had one positive element. So this is the final table for starting the simplex and solve the problem. So as you see here, this table, of course this one is our entering variable. You see here we have only 4 columns. Okay, and dividing the right hand side by the positive values of the pivot column, the minimum one is the pivot number. That here it means that x5 enters, okay, while x3 leaves our basic variables. Okay, one important item, guys. Some of you ask me that in case of having minimization, what happens to the leaving variable? It is totally indifferent. As I told you in the class, in both cases, we divide the right hand side by the positive values of the pivot column and we select the minimum amount, minimum number of these divisions. So after one iteration, this is the table that we have in our problem. What happens here, guys? You see in the row of z, we don't have any negative numbers, okay, negative numbers, and the problem is totally optimal. So what is the total value of optimal z? So we know that minus z star is minus 5.25. Okay, so as we discussed, we calculated this one in case that we change minimization to maximization. So our z star is 5.25. As you see here, guys, we improved our solution to find the optimal solution. So this was the explanation of the two-phase method. Always the process is something like this. Okay, I hope this video helps you to understand better all the topics. Have a nice time and see you later. Bye bye.